if you add those together, and we'll talk about how you can do that. If it's one-dimensional, it's all in one line, motion's all in one line, then they're just numbers. You just multiply these, multiply those, add them together. That is the total system momentum, or you could say the sum of the momentums. I'll just say total, say T. The total momentum for the system. We think of them as a system. And the idea is that this total is going to be the same even after the collision. You will still have mass 1, but now you're going to have a different mass or velocity 1. I'll put a little tick mark by it to show that it's different. And mass 2 will be the same, but its velocity will be different. They're now moving out away from each other rather than towards each other. So I put a little tick mark by the new ones after the collision. But the idea is that whatever it is, they're going to add up to be the same as they were before. So if I can take the before situation and figure out the total momentum, that is a number, and these two things will add up to equal that number, no matter what. The problem is I have two unknowns and just one equation. So you can't really solve that unless you knew one of these numbers. So the problems that you're always going to be getting is, okay, here's two objects before they crash. From that, you calculate the total momentum. Then they'll say, okay, here's after the crash. One of the objects does this. They'll tell you one of these. What's the other object do? And so you'll plug it in to this equation. You'll say, well, I know the total from before. So that equals this mass times an unknown plus this mass times the given. So you can solve it that way. Maybe we'll do one of those right now. So let's say I have these two objects that are moving towards each other. Let's say the first object is a 10 kilogram mass, and the second object, well, is a 5 kilogram mass. They're both moving at 2 meters per second to the right. Well, what am I doing? 2 meters per second to the right. This one's going to be moving 2 meters per second to the left. So I'll say minus 2. And they're going to crash into each other. Ooh, excuse me. Let's say after the collision, the 5 kilogram object is now moving to the right. Let's say 4 meters per second. So they crashed into each other, and then the right one, the smaller one, bounces away quicker. What's the 10 kilogram mass doing? Sorry, it's windy and there's a door that's repeatedly slamming. So you're going to set this up. You're going to try to find the before total. So that's 10 times 2, because it's a 10 kilogram object going 2 meters per second. I'm going to add to that the 5 kilogram object traveling at -2. And that's going to give me a total momentum for my system before the collision. So I have 20 minus 10 here. So I have a 10. The units would be kilogram meters per second, but 10 would represent my momentum for my whole system. The whole system together has a momentum of 10. The parts, this part on the left has a positive momentum of 20. The one on the right has a negative momentum of 10, which the positive and negative is just the direction. And when you put them together, the whole system has a net momentum of 10 to the right. Okay, so after the collision, we know they crash, and that we know that one is moving to the right at 4 meters per second. So I'm now gonna redo that, but I'm gonna say, here's my 10 kilogram object. I don't know how quickly it's moving. I'll say V2 prime or something. Or you could just say V. It doesn't matter when you're looking for one thing. So I don't know how quickly the 10 kilogram mass is moving or in what direction, but I do know that the 5 kilogram mass is moving at 4 meters per second. And altogether, the system still has, because it's a conserved quantity, it still has 10 units of momentum. Well, this is 10 times V. This is 20. So let's solve for V. I'm going to subtract 20 from both sides of the equation. And I get 10V is equal to minus 10. If I divide 10 on both sides, you'll see that V is minus 1. So I now know that after the collision, the 10 kilogram object will be moving at 1 meter per second to the left. Did you guys follow that at all, or okay? Good, good. So those are pretty straightforward. Momentum's not hard to calculate, especially if you're doing one-dimensional motion. You just add it up for the system beforehand. You know that quantity is going to be conserved, so it was 10 before, it's going to be 10 after. And then you go to the after scenario, and you plug everything in that you have. There should be just one unknown at that point, and then you solve for that. And that's how you always answer those questions. So that was momentum, the conservation momentum. There's another scenario where that's used. Let me get rid of some stuff here. I kind of want that. I'll put this off to the side. I didn't get that, did I? The Newton was that. I don't think we need that. Oh, maybe. No, not today. And this can stay. Actually, all this can stay. Okay, so I'm going to duplicate some of this. We'll come here. So this was for collisions. And this was for explosions. An explosion is kind of like a collision in reverse. That's kind of the way we think of it. Well, let me come back to the explosions actually. I want to go over a couple types of collision first. Yeah, there you go. Maybe I'll duplicate that. Flip that. Okay. No. Weird. All right, so just the momentum before and the momentum after are the same. The total momentum. There's a couple types of collisions. There's the case when you have here's the two objects. One hits the other one. Let's say they both come together, and let's say they have the same speed and the same mass. They're coming together. They bounce off each other, and other than the fact that they turned around, they still have the same mass and same speed. Nothing's slowed down. Nothing's changed. If that's the case, kind of like you had two rubber balls and they hit in the air and they bounce away. That's possible because when they hit, the balls are able to deform, and then they sort of bounce back. They restore, so there's no permanent deformation, and that's called an elastic collision because they sort of get all the energy back out. I should be talking about momentum, but those are called elastic collisions. An totally inelastic collision would be when it's like you threw Play-Doh at each other and they hit in the air and they just sort of stuck together. So they became one ball of Play-Doh. If the things collide and stick together, that's a completely inelastic collision. Alternatively, you could throw Play-Doh at a bouncy ball. They may not stick together, but the bouncy ball and the Play-Doh might not fling apart at the same speed that they did before, partly because the bouncy ball could restore after its deformation back to its original shape, but the Play-Doh may have been permanently deformed. So even though they don't stick together, that would still be an inelastic collision because it's not the perfectly elastic case where they don't lose any speed, I guess we could say. Now, an explosion is kind of like an inelastic collision in reverse. So you have those two Play-Doh things and they strike each other and then they're stuck and then they're together. We'll play the film backwards and you'll see two things stuck together and then all of a sudden they fly apart. It's the same thing. We also deal with explosions using these conservation momentum laws. The idea being that I wish I had good graphics. Let's say I've got, I'll try to duplicate this and cut it. We'll go like so. So I can do that. And I can do this, sort of. Okay, whatever. That one gone. Okay, here's my little ball. And the idea is that this thing, let's say we know its course would be like this. Well, straight line. You get the idea. And this object, we look at its center of mass, and it's going to follow that line at a constant speed. But at some point, you hit the detonator or something, and it blows up, and a piece flies off, and this part flies away. As time goes on, maybe I should have done it like this. And then it breaks. And then the next moment it's further. The next moment further still. And so it breaks apart. The idea with this, it's not just the conservation of momentum also tells us that we're able to calculate something called the center of mass. And we'll later go into how that can be done. But there's this center of mass for the two parts. Let's say it's at the center of the circle. And you can calculate the center of mass for two objects. It's basically just kind of like a weighted average of their position.